Hello, good evening, everyone. Okay, I see quite a few people here. That's great. Right, so please, the first question is a traditional question. So how many questions from physics have you managed to do? And one, no, right. Math one, okay. I've been doing more of the math so far, okay. Please note that our students typically say physics is harder than maths, so just be aware. Leave plenty of time for physics. But the question was how many questions you managed to do from physics. Okay. Good. Alright. Okay, so that is that makes sense. You still have plenty of time. You have just under a month to finish it. So yeah, and there'll be more webinars. There'll be at least there's going to be one more webinar on maths on the 27th, then a physics on the 4th, and then another one on the 11th. I don't know what I'm going to do. I'm probably do physics again, or maybe a mixture of maths and physics. It depends on how it goes. Amazing. So let's dive into some vectors. Vectors are incredibly important, and what we do is we give you maths, which those parts of maths that are important to do when you're doing physics. But this topic, vectors, is so important that we've put it into physics. And the topic is called vectors in physics because vectors play a massive role in studying physics. I'll share my screen. And yeah, well, I mean, just for you to understand, you probably know this equation. We'll do this later on. S is equal to ut plus 1/2 at squared. You recognize this equation, right? I assume you recognize it. If you don't recognize it, type a 0 in the chat. If you recognize it, put a 1. Well, you didn't need to put anything. I assume you know it. So I had just 1 or 0. It's a Suvat equation. It's one of the topics that you do. So S is displacement, U is initial velocity, T is time, 1/2. So this is one of the most important equations. No, so this equation is not in the assignment. This equation is from school. But there's a grown-up version of this equation, and the grown-up version looks like this. And we're going to study this in November. So it's a vector which depends on time. It's a vector function of t, which is equal to the initial position of the object plus the initial velocity, which is u, which is also a vector multiplied by time, plus 1/2 multiplied by acceleration, which is also a vector multiplied by t squared. So this is the grown-up version of this equation, and we will study this in a couple of weeks' time. So look, even this Suvat equation, it's actually initially written in vector form. That's how important vectors are. And for example, if you study pretty much anything in physics, it's mostly to do with vectors. So what is a vector anyway? You probably had vectors in your GCSE math course. So a vector is a pair of points, or we can say a vector is 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 a directed right. R0 is the initial position. Initial position. Vectors have magnitude and direction, of course. The magnitude is the length of the vector, and the direction is the, well, direction. Nicholas, you're asking good questions. Let me get back to that. A position vector. It's actually in the assignment. So a position. All right. Describe the basic operations on vectors. Okay, yes, if you can't hear me, do exit and try again. So adding vectors. So a vector is, a vector is a line segment which has a direction. We could describe it like this. Sometimes a vector is described as a pair of points. So sometimes a vector is defined as a pair of points, like x and y. This is a vector. In physics, vectors have magnitude and direction, so it's a value. We don't do vector proof. No. It depends on what you mean by vector proof, but yeah. Okay, so if you have a vector A and you want to add it with a vector B, so vector A and vector B. How do you do it? Well, there are two ways to do it. Equals. You can do either. So there's a symbol for or. So this bracket in maths means or. So if you see it used, for example, x is equal 3 or 2. That means x is equal to 3 or equal to 2. So just we sometimes use this. I don't know what's going on. Why is capitalized? No, so usually we use capitals when we have A, B. When we use the start and the end, that's vector AB. But if we just use small a, we mean this. We're talking about this angle. Right, guys. I'm reading the chat. I'm getting distracted by the chat. So please, if you have questions, do ask. If you want to have a chat, that's not the place. Right. So the first way is using the triangle rule. Triangle rule. And what you do is you copy this vector. Copy this vector, and you copy this vector, and you get a triangle, and by completing this triangle, you get the total vector. A, B, and this is A plus B. Okay. Or you can use the parallelogram rule. So parallelogram rule. If you want to use the parallelogram rule, it's the same thing. You copy this vector. Copy this. You copy vector A. You copy vector B, but you copy vector B from the same point as vector A. So not from the end of vector A, but from the beginning of vector A. And then you have what you do is you complete a parallelogram. You complete a parallelogram like this. So this is a parallelogram. And you draw the diagonal of that parallelogram. The diagonal of that parallelogram is vector A plus B. So this is vector A, this is vector B, and this is vector A plus B. So two rules, they are effectively the same, and you can see that the result is the same. Yeah, there's nothing new here. A is this, B is this, A plus B is this. Here, A is this, B is this, A plus B is this. Does that make sense? On a scale of 0 to 10, please, a quick vote. Do you understand the triangle and the parallelogram rules? Okay, very good. That's great. That's great to hear. Multiplying vectors. When I say multiplying vectors, I mean multiplying vectors by a scalar. Forgot to mention that. If you want to multiply a vector by a scalar, well, yes, that you just multiply the length of the vector, keeping the direction the same if the number is positive, and keeping the direction the opposite direction if the direction is opposite. So if the number is negative, sorry. So this is A, and this is KA. KA if K is positive, and if K is negative, it's the opposite direction. So this is I don't know, MA, where M is negative. So that's multiplying a vector by a number just simply increases the length of, well, multiplying a vector by a number just changes the length of the vector, doesn't necessarily increase it. What about tip to tail? Is this the triangle rule again? Tip to tail is the triangle rule used several times over. So for example, if you have, let's call it tip to, if you have three vectors, that's a valid point actually. So if you have a vector like this, a vector like this, and a vector like this, and what you do, and let's do another one, and a vector like this. So what you do is you copy this vector, and then you copy this vector. Now note that the order in which you do it doesn't matter. You do this plus this, and this gives you the vector. You can imagine that there's a vector going from here to here, right? And then you add the third vector. You add the third vector, which is here. And you can imagine that this is just like adding this vector, which is the result of adding the first two and this one, which gives you this vector. And then you add the third vector in. You add the third vector in, and a fourth vector in, sorry, fourth vector. And then you get, it's just like adding this red vector plus this blue one, and the total is this vector. So it's just The tip to tail method is the using the triangle rule over and over again. Triangle rule and parallelogram rule are the formal names. Tip to tail, yes. Triangle rule. When finding the result, you have to do tip to tip. So if the scalar is negative, it flips the direction. Yes. And if the scalar is 0, and then it just becomes a 0 vector. A 0 vector is just a point. And an interesting thing about the 0 vector, a 0 vector is parallel to any vector. Also, a 0 vector is perpendicular to any vector. Okay, so that's an interesting fact about zero vectors. Subtracting vectors. Subtracting vectors is an interesting method as well. So what do I do with this? Okay, let's make proper notes. So this is A, B, C, D. This is A, B, C, D. And this is A plus B plus C plus D. So adding multiple vectors. So multiplying vector, multiplying by scalar. Then we have adding multiple vectors. Adding multiple vectors. All right. Subtracting vectors. Subtracting vectors is an interesting one. Subtracting. By the way, I haven't mentioned that, but I have already, because COMPOS is running for 3 years. It's the 3rd year we run COMPOS. So I have already done 3 webinars, 3 full 1.5-hour webinars on vectors. And I have done questions which are very similar to the assignments questions. So you can view those if you just go to our YouTube channel and so really, that's how you do it? No, that's not how you do it. That's how you do it. Your channel. So this is our channel where you can access all the recordings, and yeah. And as you can see, we have 4 playlists. So COMPOS webinars, that's year 12 from the 1st year we've done it. COMPOS year 12 webinars, that's the webinars from last year. And COMPOS year 13, well, you don't need that for now. You'll need that next year. And COMPOS year 10 webinars, we've just started, and we've only done 2 so far. And as you can see, COMPOS year 12, we have 42 webinars plus 37. So overall, we have 77 webinars recorded for year 12 COMPOS. So please have a look. And subtracting vectors, would you just flip the direction of one of them? Yeah, that's very good. Yeah, that's what you do. That's exactly what you do. Subtracting vectors. So you have a vector, for example, vector A, vector B, vector A, vector B. Now adding a vector, so you say add A minus B, well, it's the same as doing A plus negative B, right? subtracting a minus b is the same as a plus negative b. So what you do is you write a vector negative b. So the vector negative b is this. This is minus b. So you take the first vector, which is vector a. You take the vector minus b, and you add it. You can use the triangle rule. I'm going to use the triangle rule, or you can use the parallelogram rule. I'm using the triangle rule, and the result is this. This is vector a. This is vector minus b, and this is vector a minus b. Right. Now, there is a shortcut. I'm not sure there's a name for this method, this shorter method. How to subtract two vectors. Basically, you draw the two vectors from the same point. Shortcut, shorter method. And if you want to subtract, then you do, so this is a, this is b, like a plus b is going to be like this, right? Using parallelogram method, this was going to be a plus b. But a minus b is going to be this, a minus b. It's the other diagonal of the parallelogram. If you think about it, it's the other diagonal of the parallelogram, and this is a minus b. So you're stretching it from the end of a to b, and this is a minus b. And the opposite vector is going to be b minus a. Yeah, if you think about it. If you have this is going to be b minus a. So this is a minus b. So this is a neat practice, neat practice, because if you have vector c and vector d, this vector is going to be c minus d. It's very easy to use if you don't get confused, because it's very easy to get confused. How do you decide the direction of the resulting vector? Well, it goes from the first one to the second one. So from the positive to the negative one. So I mean, the end of the vector corresponds to the end of the vector you're subtracting from. There's no beautiful rule that you can memorize. I don't know. Think maybe you can invent a mnemonic. So I'm very sorry. I just pop out for 30 seconds. Just a All right. you do have to understand it. Yes, because you would. Well, one way of memorizing it is this. So, for example, if you have, there was a question about the position vector. So let me answer the position vector first. A position vector is a vector drawn from the origin to a given point. The position vector of a point, the position vector of a point. Position vector in physics, we use R is the position vector. Sometimes R of t, if the object is moving, that means the position is changing. R or R of t, because it's a function of time. So you have, let's say you have a point A, and you have the origin. Origin is, well, where x is 0, y is 0. The vector drawn from O to A is called the position vector of A, or radius vector. So R is the radius vector, or aka position vector. So for the position vector of point A is effectively equal to the vector OA. Now, in maths, you probably have learned that if you have point, if you have a point A, and you have a point B, to find the vector BA, you need to subtract from the vector OB, you need to subtract vector OA. So O is the origin. So BA, the vector BA is OB minus OA. And if you remember this, so this is the position vector of B, and this is the position vector of A. This gives you an idea that, oh yeah, it does make sense. So vector AB is vector OB minus OA. The x and y components of the position vector would be just the coordinates of the point A then. Yes, very good. Well done. Good. So what are we up to? Subtracting vectors, subtracting projection of a vector. I've used a lot of space here. Okay, let's see if I can move this. Projection of a vector. Projection. A vector. Projections are very important. So for example, if you have a vector like this, and you have the x-axis, so let's say you have the x-axis. This is the x-axis. Then the projection of vector A, so this is vector A, the projection of vector A onto the x-axis is the shadow of vector A. If we imagine you have some light coming from the top, the shadow of vector A on the x direction is called the projection of vector of a ax. So ax is simply the length of the projection, but ax with an arrow, that's a vector. It is. It is exactly the x component of a. But the thing is, it doesn't have to be on the x-axis. It could be a projection on something else. So, for example, you can have a projection of vector A onto any line. So the projection on an x-axis is usually A cos alpha. So if you have an angle alpha, so modulus of AX is equal to modulus of A cos alpha. That's a typical situation. So AX is a projection of vector A. A component is a projection of vector A onto the x-axis. Do you need to understand that the projection is deeper, is more sophisticated than that. So you can have a projection on any line. So for example, you have a projection, you have a line and you have a vector like this. So a projection of a vector is the shadow of this vector on the line. So if this line is L, this would be the projection of vector A onto line L. Usually that's the notation. The modulus is just the absolute value, the magnitude. And so finally, the modulus of a vector is the same as the magnitude, so it's the length of a vector. It's the length of a vector, and for a column vector, for example, so modulus of a vector, modulus of a vector, simply its length. Modulus A is the length of vector A. It's also known as the magnitude. Do we draw the dotted line depending on the light? It's always perpendicular to the line. The shadow is the same angle as the angle being projected onto. If that makes sense. If is the shadow at the same angle as the line, well, it's perpendicular to the line. So these lines are always perpendicular. So it's an it's actually called an orthogonal projection. That means right. Orthogonal means right angles. So this is a vector, and this is the projection of this vector. So it's the component of vector A in the direction of line L. That makes sense. So a modulus of vector is simply the length. If vector A is equal to x, y, then the modulus of A is the square root of x squared plus y squared. Why would the y component be sine A? Yes, absolutely. The y component would be sine. All right, so I really hope I haven't confused you with this. This is just definition, so we're just going through what are vectors, what do we use them for, and Well, actually, that's a very good question. What do we use them for? And it's an important question. Like, why do we use vectors? So a vector is usually used to describe the position of an object. A vector is used to describe the position. So R of t is the position of an object. So let's do an experiment. So position bet projector. You will be studying projectile motion if you haven't already. Okay, so let's throw a piano and shoot a piano. Okay, perfect. So let's shoot a piano from 0 initial height at an angle 40 degrees and 25 meters a second. Okay, we need to zoom out. You know what? No, I want to slightly higher. And that looks good. Okay. See if we can hit the target. Nope. Right. Anyways, if I shoot, look at this. When time is 0.2, I'm here. When time is 0.3, here. 0.4, 0.5, 0.6. So when time is 0.6, the position of the piano is here. So let's take a screenshot of that. The magnitude of the original vector, usually not. It's the same only if it's parallel to the so what are we doing here? Here we have the x-axis. So this is the x-axis. This is the y-axis. And this is the position vector of the piano. So it's the position vector when t is 0.6, 0.7, 0.8, 0.9, 0.1, 1, 0, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. So this is 1.6. And if we draw this is the position vector of r when t is 1.6. So as you can see, this is a function. So r of t is the position of the piano at time t. And this is incredibly important. It's a very powerful concept in physics. No. Yes. Not necessarily. This is called modeling. Yes. Well, it is called modeling. Absolutely. What is called what is the definition of a position vector? Position vector is the vector drawn from the origin. So the origin to the current position of an object. position vector of the piano is a vector drawn from the origin to the current position. You can work out this vector because you have the range and the height. So basically this vector r 0.6 is equal to 13.6 and 13.6. Interesting. Funnily enough. 1.6, well, we can work it out. We can look it up. Let's see. 1.6. It's 36.2, so 36.3 and 13.4. The magnitude of R06 is not the x component. The magnitude of the vector r is the square root of x squared plus y squared. Charlie, it depends on what you want. If you want the position relative to the origin, then no, you don't. If you want the position relative to the canon, if the canon is your origin, then yes, you do. But but you usually measure from the origin, not from the canon. It's just in most questions the canon is at the origin, and then it makes life simple for you. But yeah, it's slightly more sophisticated questions that you measure from the origin. So do you understand what a position vector is on at least on an intuitive level, on a scale of 0 to 10? Do you understand what a position vector is? So the position vector, right? Okay, so quite a few 6s, 7s, and 8s. Position vector is a vector that follows the object. It's always drawn from the origin. So it's like, I mean, if you throw something at an angle, the position vector, it just changes. It's like this, then it's like this. So at any given time, the position vector is this. You don't, as long as you understand this, it is fine for today. Okay? Because we'll go deeper into position vectors in its next assignment. So as time changes, the position vector changes, of course, and it just gives you the, like, literally, if the position vector, like, let's say the position vector is if the position vector in this particular example, if the position vector is, I don't know, 3, 4, that means it is 3 meters away horizontally. It's 3 meters away horizontally, and the height is 4 meters. That is the height above ground. So we can say the position vector of this human, which is here, is about well, probably 6, 0. That's the position vector of this human. The position vector of the cannon. What's the position vector of the cannon? Somebody help me. 0, 9. Yes, well done. It is 0, 9. It's the coordinates. The position vector, effectively, it's the coordinates. It's a vector made with the coordinates as yeah. Okay, good. So yes, I think we can establish the position vector. Okay. Describe how the scalar product What describe the scalar product and how it is linked to the projection. And this is an interesting one. So looks like today I'm going to do about half of the session on theory and half, maybe even 2/3 on theory. But please do that. In the previous one, in the previous years, I did more on problems. So if you want to see more problems, go back to our previous recordings. The scalar product and how it is linked to a projection. So you have the scalar product is defined. So A, the dot product, B, is modulus of A multiplied by modulus of B multiplied by the cosine of the angle between them, cosine theta. What does that mean? Well, if you have a vector A and you have a vector B, vector A, vector B, the scalar product is the length of vector A multiplied by length of vector B times the cosine of the angle between them. This is the definition. Maybe. You understand? Can a vector be represented as a coordinate? Coordinates. A vector is a pair of points or a pair of numbers. So it's a position vector consists of the x coordinate and the y coordinate of the object. So a vector is the point, and a point is a vector. In a way, is a point a vector? A point is not a vector, but you can, because a point has a position vector. I hope that makes sense. A dot B is not a line. A dot B is a scalar. That's why it's called a scalar product. So A is a vector. A and B are vectors. But A dot B is a scalar. That means it does not have a direction. A zero vector is a vector. Well, I mean, by all means, it is a vector. A zero vector is usually drawn O the dot, so it's equal to 0, 0. Scalars are just numbers. Scalar, any like 3 is a scalar. Scalars are just numbers. Because a vector is a pair of numbers. So for example, 0, 0, 0 is a vector, but 0 is a scalar. So there's 0 vector and 0 number. So a scalar, a vector is always a pair of numbers. A scalar is just one number. Well, no, it doesn't work like that. It depends on the angle. So if the angle is 90 degrees, for example, the scalar product is 0. If theta is 90 degrees, then theta is 90 degrees, then A dot B is 0. This is one of the most important properties because cosine 90 is 0, therefore A times B is 0. Okay, so let's say we have a dot B, the scalar product can be negative. A vector cannot be positive or negative. And that's sort of a paradox, because in school you're taught the opposite. You're taught that vectors can be negative vectors can be negative and scalars can't. Yeah, if you remember, like a speed can't be negative, but a velocity can be negative. Now this is a slight misinterpretation of vectors. So it's just when the vector is going backwards, we say it's a negative vector. But a vector itself, well, it can't be negative. Like, honestly, it can could be in the opposite it could be in the negative x direction. When we say negative vector, we mean a vector in the negative x direction or negative y direction. So, but technically, a scalar can be negative, but a vector cannot be negative. Oh, that's this doesn't help at all, does it? Okay. Oh, yeah. Right. So let's have a look. This is the definition of scalar product. Now, yes, I'll do an example. I'll do an example first. Example. If you have a box and you apply a force to that box, let's say a force which is equal to, I don't know, 4 newtons. So force that's in newtons, 4. And the as a result of that, the box moves, and the displacement of the box, S, is the displacement of the box, and it's equal to, let's say it's equal to 10, it moves 10 meters. Okay. Well, in order to find the scalar product, we need the magnitude of F. So what's the magnitude of vector F? 5. Well done. The magnitude of F is 5. So the force is 5 newtons. What's the magnitude of S? 10 meters. And theta, well, we don't necessarily need to find theta, but we can find cos theta. If we draw a line like this, so this is 5, this is 4. So cos theta is equal to 4/5. So the dot product of force multiplied by S is equal to force dot product of F times S is equal to modulus of F multiplied by modulus of S multiplied by cosine of the angle. So it's 5 multiplied by 10 multiplied by 4/5, which gives us 40. And so, yes, thank you for explaining how you get 5. That is work done. That is work done. So it is work. Work is defined as the scalar product of force times distance. So that's 40 joules. That's the work done. Work done. So in physics, the work, which is a scalar, is defined as the dot product, is the scalar product of force and displacement of two vectors. But you can also do this in the following way. You have force multiplied by S. You can use the formula. So it's 3, 4. So it's 3, 4 multiplied by 10, 0. Ooh, where did I go wrong? Of course, I went wrong here. This is 3, 4, not 4, 3. So this is 3. So I've messed up. Sorry. So it's 3/5. So it's 3/5, and that's 30 joules. That's 30 joules of work done. So you multiply F by S. F by S is 3, 4 times 10, 0, and that makes it 3 times 10 plus 4 times 0, which makes it 30 joules. 30 joules of work. So the work done is 30 joules. Does this example make sense to you on a scale of 0 to 10, please? So you can, I've done it in two different ways. I've done it using the definition of the scalar product, and I've used the formula for the scalar product. Okay. Brilliant. So now, what is the link between the scalar product and the projection? And that's a very intricate one. So bear with me. Imagine you have a vector. Imagine you have a vector b. And imagine you have a vector a. Vector a. The dot product a times b. A times b. By definition is modulus of a multiplied by modulus of b multiplied by cosine of the angle theta. So theta. But if you draw the triangle here, this is a, this is modulus of a, this line, but this is modulus of a cos theta. So if you have, so how to put it in easier terms? So what I'm trying to say that a cos theta is the projection of vector a onto vector b. Do you see that? Yeah, this is because this is the adjacent side of the triangle. It's the adjacent side of the triangle, and so A cos A projection. So basically, the scalar product is the length of vector B multiplied by the projection of vector A onto B. So let's say we make vector B, instead of vector B, we take a vector of length 1 in the same direction as vector B. So yes, you can write vector A, B, the projection of vector A onto vector B. Like this, B A index B. This is the shorter way of writing it. So if the modulus of vector B is equal to 1, so basically that B is a unit vector, unit vector, then A dot B is a projection of A onto B. So basically, the scalar product in some cases is a projection. That's the link. That's the link. And if B is not equal to 1, then you can modify if B is not equal to 1, then all you need to do is just divide that by the length of B is a projection of A onto B to B. Hope that makes sense. Right. So this is the link. So don't worry if you don't fully get it. I don't think we have any problems on this topic. So don't. But it's very nice if you do understand the power of the scalar product. So first of all, it's the work done. Second of all, it's the projection of one vector onto another. Yes, A and B are interchangeable by all means. So the projection of B onto A would be B times A over. So we can write, in short, that the projection of A onto B is equal to A dot B over B, and the projection of B onto A is equal to A dot B on A. Can position vectors can be expressed using I and J? Yes. Usually it's lowercase. Sometimes we use capitals, but very rare. Usually it's lowercase. Okay, so now a few simple questions. They are quite simple. So modulus of A equal. So this is a problem from MIPT, and the A is vector A is 3 and lambda. The modulus of so 4 is one of the answers. Yes. So we know that modulus of A is equal to square root of 3 squared plus lambda squared. That's how it works. We had this above. MIPT is Moscow Institute of Physics and Technology. And so this is equal to 5. This is the university I went to. And so yes, and so that is that. So 3 squared plus lambda squared equals to 5. We square it, so it's 3 squared plus lambda squared equals 25. Lambda squared equals 25 minus 9. So lambda is equal to plus or minus 4. Now, there are no limitations that lambda is positive or negative. So you have to find both values. So the answer is that. No, MIPT is the name of the university. And this is a problem form that they give to their students. Well, yes, sort of an entrance exam. I mean, this is slightly easy for an entrance exam, but it's a question which was written at that university. Okay, vectors A and B. So A is 0, 3, and B is lambda 5 are collinear. So find lambda. So they are collinear. Well, what does that mean? Well, vectors are collinear. We write A is equal to, collinear, basically parallel to B. It means A and B are collinear. Or parallel. Yes, they have the same gradient, or they have this. They are simply parallel, and vectors are collinear. So A is parallel to B if you can write A is equal to K multiplied by B, where K is a number, is a real number. This is the definition. So what does that mean? Well, that means there exists a number K that can be written. Well, example, 3, 2, and -6, -4 are collinear. Because if you multiply the first vector by -2, you get the second vector. K could be 0, yes. K could be 0, but that's what we say. A 0 vector is parallel to any other vector. Is collinear to with any other vector. So these two vectors are collinear because 3, 2 multiplied by -2 is -6, -4. So if you can find a number that you multiply the first vector by to get the second vector, the vectors are collinear. And so we do this. So vector B is equal to Ka. It doesn't matter which way you do it, by the way. Yes, because it's symmetrical. Lambda 5 is equal to K multiplied by 0, 3. Oh, I didn't realize that the answer was 0. Yes, yeah, of course it is, because that's the only possibility. So 3K is 5. 3K is equal to 5, so you can work out that K is 5/3. And you multiply 0 by 5/3, and of course you get 0. So lambda is 5/3. Oh, let's lambda is k multiplied by 5/3, which is what? Yeah, sorry, k times 0, which is 5/3 times 0, which is 0. So lambda is 0. I don't believe I can't believe I missed it. And it's actually 0. It's super simple. But yeah, it doesn't have to be 0. It could be something else. It could be something 0 if vectors are perpendicular. Would they be perpendicular? No, they're perpendicular if the scalar product is 0. A is perpendicular to B if A dot B is 0. Okay? And this, ooh, I got a tough question for you. In maths, we have two symbols. We have the symbol this, that means if, yes, that means if, then. And we have this symbol. That means if and only if. And only if. If and only if. Yes. So it is appropriate to put this symbol here, but it's not appropriate to put this symbol in. Can somebody tell me why? So if this is true, then this is necessarily true. But if this is true, this is not necessarily. Oh, no, it is. Sorry. I'm just speaking rubbish. No. I was, it is appropriate. I'm very sorry. Ignore me. I think I'm getting a bit tired today. It's perpendicular. That means perpendicular or orthogonal. If A is not 0, but B is 0, B, 0 vector is facing all directions, so it's perpendicular to any vector. Okay, so here it is. These are vectors are perpendicular, so find lambda. So we know that A times B must be 0. Therefore, this the symbol, you will see it a lot in the assignment. So that's what it means. Therefore, or it also means if then. Therefore, -1, 3 dot lambda 5 is 0. We multiply, so it's -1 times lambda plus 3 times 5 equals 0. And you can work out minus lambda plus 15 equals 0. Lambda equals -15. Cos 270 is 0, yes. But I don't understand how is this is relevant. Why 5/3? Okay. Because I've proved that here. Now, so the dot product is modulus A, modulus B, cos theta. If theta is 90 degrees, so if vectors are perpendicular, that means the dot product is 0. Does that make sense? What was asking? If so, the two vectors are perpendicular, the product, the dot product, because we have other products of vectors. We have a vector product, which is not the same as a dot product. So yes. Just a other product. So we have the cross product, also known as a vector product. Vector product. And it's written like this: A cross B. So this is not the same as A dot B. So with vectors, these are very different. So this is a dot product, this is a cross product. More to that, a cross product is a vector. So this is a vector, and this is a scalar. And we also have the mixed product of vectors, which I won't go into, but you'll encounter it in the further maths course or university course. Okay, so we have just actually 3 questions. Two of them were labeled question 7. Actually, I went through this problem last year. So see video from comp video from 609. See video 609 and 2009. See 06, 09, 22 and 20, 09, 22. So okay. So the solution is there. One of them, I don't remember which one, but you can quickly skim through and see which one it is. See webinars. So I won't do this again. Find the angle between the vectors. So here you can see that the vectors are done as i's and j's. So I don't like i's and j's, honestly. Whenever I see i's and j's, I just write 3, 2. Because it's just, for me, visually, that looks better. -2, -1. Find the angle between the vectors. So how do we do this? Well, we know that A dot B is equal to A multiplied by B multiplied by cos theta. Well, we can work out cos theta from here. So cos theta is equal to A dot B is the dot product divided by modulus A modulus B. No, ij not complex numbers. So I is the vector 1, 0. and j is the vector 0, 1. That's another reason why I don't like i's and j's, because they're easy to confuse with complex numbers. So this is a vector. So in fact, you typically draw i's and j's. So you can show that if you add 3 of these vectors and 2 of these vectors, you get 3, 2. Yeah, 3 of these plus 2 of these actually makes A. Right, so if you want to cosine of the angle between 2 vectors, well, you just use this formula. So this is vector A, this is vector B, and yeah, so by the way, some vectors can be written like this, can be written like this, can be written like this, sometimes can be written like this, and this usually means normalized vector, as in unit vector. But it has to be defined. If you're writing it, if you're reading a paper, it has to be defined what it means. It's not universal. And okay, so that's cos theta is that. So A times B, so you multiply the 2 vectors, so 3, 2, multiplied by minus 2, minus 1, divided by modulus of A. Modulus of A is the square root of 3 squared plus 2 squared, multiplied by square root minus 2 squared plus minus 1 squared. And 3 minus 2, so it's 3 times minus 2 plus 2 times minus 1. With that, and that's square root 9 plus 4, that's square root of 13. Multiplied by, that's 4 plus 1, square root of 5. Is it? Yeah, square root of 5, which makes it very, very good. Harris, thank you. It is minus 6 minus 2, so it's minus 8 over square root of 65. And theta is approximately, well, cos negative 1 of minus 8 over square root of 65, which is approximately, it's equal, this is equal, but this is approximately 173 degrees. So there you found the angle between 2 vectors, and which in fact is an obtuse angle, so that's perfectly fine. That's 3 significant figures. Oh, what do you mean? This is the definition of scalar product. This is the definition of scalar product, and we just rearrange it to find cos theta. This is definition. All we did is we divided both sides by modulus A modulus B. Does that make sense, Karim? Okay. So Abiola, A cross B is a cross product, and the result is a vector. And where is it? If A dot B is equal to modulus of A multiplied by modulus of B multiplied by cos theta, then A cross B. Well, there are different ways to do this. The least is modulus of A multiplied by modulus of B multiplied by sine theta. And now this one is horrible. Multiplied by the normal vector, which is obtained, which is perpendicular to A and both A and B, and in a direction such as A, B, and N make a right triplet. So this sounds horrible. Look it up. Look up vector product. So it sounds worse than it is. Another way to define the cross product is this A dot B. So if vector A has coordinates A1, A2, A3, and B has coordinates B1, B2, B3, then the cross product is I, J, K, which are vectors, is the determinant of the matrix A1, A2, A3, B1, B2, B3. So yeah, there are other ways defining cross product, but you can see a reason why they don't give you cross product in year 12. It's not easy. Right triplet. No, that's not a right triplet. A right triplet is a right. That's not what I mean by a right triplet. So basically, if you have two vectors, A and B, so vector A and the vector B, and this is in 3D. This is in 3 dimensions, A, B. If you turn A to B, and it's a clockwise rotation, then the vector n is like this. Then the vector n is like this. So this is a right angle, and this is a right angle. I don't want to go further into this. I literally have 2 minutes left, and I wanted to go through another problem with you. No, it's not like bearings. Vector, what is it? A vector product. Yeah, this looks like a good one. I think I know this one. I know this channel. Yeah, you can have a look. It's it's not an easy it's not a concept I want to go into right now, like honestly. All right, so problem 8, a small aircraft. So I've also done this question last year. So um, if you need to go, you can watch last year's video. It's a very similar one. A small aircraft landing speed is 60 knots. And there's a steady crosswind of 50 knots. How should the pilot direct the plane in order to fly in a straight path? What if the crosswind is 17 knots? So this is linked to the boat and the river and the boat question, and it's also linked to the hardest question in the. It is like Fleming's left-hand rule. Yes, Abiola. Thank you. It's also linked to the hardest question, which is the river crossing. The hardest question in the assignment. So you have an airplane, and we are looking from the top. So the airplane is coming into land. So it looks like this. Slightly bigger airplane. So it's coming into land. We're looking from the top, and this is the runway. On the runway, they have numbers always. So for example, 20, 20. You might have seen the runway. Does anyone know what the numbers mean? It's a bearing, yes. So 20 means a bearing of 200, basically. So the number 20 means bearing of 200. Number 30, so 20 means bearing of 200. 13 means bearing of 130. That's and I don't understand the reference name. So. Is that from a movie? Anyways, so a plane is coming into land, and the speed of the aircraft. So what happens if there's a crosswind? So this is the speed of the aircraft. Oh, okay. This is the speed of the aircraft. So there's a crosswind going this way. So what happens if the plane directs this way? Well, it will be blown off the course because the velocity of the plane plus velocity of the wind will cause the plane to drift sideways. They will fly this way. This is not good. Basically, not good for any aircraft. So what the pilot does, the pilot actually directs the airplane this way. So this is the velocity of the plane, and the wind blows in this direction. And the total speed, so this is the velocity of the wind, and this is the direction. So in order to fly straight, the plane has to direct itself sideways. So, and your task is to find this angle. So, well, that is quite straightforward because we know that this is 60 knots. Whatever knots are, we don't really need to understand knots. A knot is about 2 miles per hour. Oh, no, it's 1.1-ish miles an hour. It doesn't really matter what it is. So yeah, I mean, this velocity here, you can find the angle. So theta is arc sine, the inverse sine of 15/60, which means it's arc sine a quarter, which is 0.25, which is 14.5 degrees. 14.5 degrees. Paris, yes, well done. But it's not. It's obviously not traveling north because we have a bearing. Now, if you're for the clever ones, work out the actual direction, the actual bearing, because we know that the runway is bearing of 200. So work out the direction, and this is pretty awesome. Like, I mean, honestly. Oh no, 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 no. This is pretty awesome because if you look at crosswind landings, partly this excites me because I have done some crosswind landings because I was training to be a pilot. Haven't finished my training. So crosswind landings, and yeah, so this is. So you can see planes approaching. Now this is a horrible situation to be in. So you can see this video that the plane is, so the runway, you can see that the runway is in this direction. This is the direction of the runway. This is the runway. way. And you can see that the plane is not pointing in that direction. The plane is pointing towards us. Well, if you draw the plane is pointing its nose in rather like this direction. Yes, slightly towards us. But there's a crosswind that blows sideways, and the plane ends up going in a straight line. And I believe that is a successful landing. Yes, it is. Okay. Sometimes they go around if you don't touch the ground well. So this is another one. Oh, that's a touch and go, I believe. So the plane is coming in. That's a what's that? A 320, A320 coming in. It's not stable. It doesn't want to touch the ground, so it decides to go around because it's unsafe. All right, so that's the idea. Now if the wind is 70 knots, like it's crazy. You would never even attempt to land at a 70 knot crosswind. That's impossible. But imagine if it was. If you imagine we are in a crazy world that there is, well, the plane would not be able to land at all because the if the crosswind is 70, even if the plane directs, even if the plane goes this way, even if the plane goes 60 in this direction and the wind is 70, it will still travel to the right. It will in no way it is able to travel along the runway. The wind is too strong. Do you understand what I mean? So even in the extreme case, you just fly left, it will still be flying right because of the wind. It can't fight that wind. Isa, I will answer your question. That's a very good one. So if you were there's no direction in which you can choose to move that will allow you to stay on track, because a crosswind of 70 would just still keep putting you on a course this way, on a disaster course. So yeah, for small aircraft, usually you never land anything more than 15 knots is just not feasible. Increase velocity, you could increase velocity, but if your aircraft is designed to land at 60, you do not want to land it at 90. It's just you won't have enough runway, the wheels are not strong enough. No, it just doesn't work. You find a runway where which is in the same direction as the wind, and then you can land. That's what you do in that scenario. Now, Isa, the wheels are sideways, that is true, but the wheels turn. The back wheels of an aircraft can turn, and they automatically, well, they don't automatically, they turn from the forces of the friction. And you can sometimes see the back wheels, they turn into the road and then they straighten out, which is quite a marvelous design of large aircraft. Right. So yes, that I'm enthusiastic when I speak about planes. Sorry, if you don't like them. Well, no, if you don't like planes, you're just a bad person. I'm just kidding. All right. Have a lovely evening. I hope you enjoyed today's session, and I'll see you next week for some more maths. All right. You're welcome. See you.